Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to have Michael Hicks visit us again from the University of Maryland. Mike was my advisor, so it's particularly great to have him here. And he's going to tell us about some new work on time travel debugging.
Thanks, Nick. OK, so this is a joint work with my student, Yit Phang khoo, and also my colleague, Jeff Foster. OK, so debugging. This work was inspired by a talk from Rob O'Callaghan at PLDI, a workshop co-located there in 2010, where he said, you guys are great at finding bugs, but we want you to stop. We have enough bugs already. We want you to help us fix the bugs. So we thought, well, there is a lot of work on finding bugs, but there's not a lot of work in the PL community on helping people fix bugs. So what might that work look like? So we started thinking about the debugging process, and we started reading about it. And as I'm sure you've thought about before, debugging is the scientific method in action. Your program doesn't work the way you expect, and so you develop a hypothesis for why that is. Based on your hypothesis, you design a test, and you predict what the outcome will be if your hypothesis is correct. You run the test. If the outcome is as you expect, then great, you've figured out what the bug is, so go fix it. Otherwise, it's not exactly what you expect, and so you refine your hypothesis and continue. And this process for trying to figure out why is the program not behaving the way I expect is, according to Andreas Zeller, who wrote the book literally on debugging, the hardest part or the most time-consuming part of the debugging process. And it's why we have lots of tools and sort of our own pet techniques for gathering the information to help us formulate and test the hypotheses. So some people will use an interactive debugger, some will use print statements, some will use profilers and visualizers, or maybe special static analysis tools or dynamic analysis tools. And record replay execution is sort of a recent tool in the tool chain to help you to do this sort of thing. Another thing that you can do when you're debugging is write scripts. So you can think in some sense whenever you stick an assertion or a print statement or something like that in your program to gather some function of the execution state of the program. Oh, look at this heap value, compare it to this other heap value, look at it over time, see whether an invariant is held. You're modifying the program, but you could just as well have written a script that somehow looks at the program execution in some way and tries to establish the information that you're interested in. And the benefit of doing that would be to avoid the sort of tedious repetition of coming up with these scripts over and over again. And hopefully also allow you to then reuse the script in a future context. Given some set of scripts that you might have designed for a particular program, you'd like to be able to compose the scripts into bigger scripts. And you might be able to link them up with sophisticated tools for doing visualization. In short, why not make the debugging process like the programming process in the first place, rather than have it be an ad hoc, do it once, throw it away kind of event? What we're going to spend as a programmer, you're going to spend lots of your time debugging programs. So why not, in the same way that we automate things like that we write programs for in the first place, help automate the process of doing the debugging to help the programmer? OK, so I don't know how many of you write scripts for debugging. How many people do scriptable debugging? OK, an overwhelming number, 0. So why is that? Well, one reason might be that scripts at the moment are fairly ad hoc. They're brittle, and they don't actually meet any of these criteria that I just mentioned up here. They tend to be hard to reuse, hard to compose, hard to even get right. So to illustrate, let me show you what it would take you to write a script to count calls to the function foo in some program execution using GDB's scripting interface to Python. I bet you didn't even know you could do that. So Python, there's a GDB extension that allows you to script GDB commands, set breakpoints, and so on. And I'm going to step through that interface here in a minute. And you can write those scripts and run them on top of GDB. OK, so the first line of this script says, I want to set a breakpoint at foo. So you call the breakpoint command to set the breakpoint. And I'm going to set 2 additional variables, count and more. Explain those in a minute. I'm going to define two handlers. The first is the stop handler, which will be called every time the function foo is called in the program execution. And the little bit of logic there makes sure that the breakpoint is due to foo. If it is, it's going to increase this count variable by 1. The exit handler is going to be called when the program terminates, and we're going to use that to set the more flag to false, which tells us to stop running our Python script. The connect functions are going to assign the breakpoint to a particular handler, to these two handlers, the breakpoint and the exited, the exit status. And then finally, we're going to start the program, and we're going to start the script, and the script is going to basically keep running the program until it's finished, at which point the count field, the count variable in Python, is going to contain all the calls, the total number of calls to foo. And then we can disconnect these and delete the breakpoint. OK, wow. So what's wrong with this idea? Well, basically, this is classic callback-style programming. And as you might be familiar with, this has several disadvantages. First of all, the control flow of the program is not straight-line code anymore. It's now smeared across the program text. So if we look here, we can't just read the code straight down to see exactly what it's doing. Instead, the stop handler is going to be called indirectly via these calls to more. So this is going to be running for a while, and then it's going to jump up here, change this state, jump back, run for a while, then maybe jump here, and then jump back, and jump here, and jump back. It's not code that you can read straight down. It's code that the control flow of the program execution is nonlinear. OK, so that's frustrating. More importantly, it's also brittle. So if the handlers can have side effects, for example, if a handler could set and remove breakpoints, then it may compose poorly with other scripts that you've written to also have these handlers, right? So for example, let's suppose I was writing a program and I had a script that counted all calls in my program execution, and I also wanted to run it alongside this script to count just the foo calls, right? I should be able to do that. I should be able to take n scripts and run them on my program execution and not worry about them interfering, except it will clearly interfere in this case because it'll destroy the all calls script. And of course, there could be inadvertent clashes on global variable names and things like this, right? So this is going to hurt our ability to reuse scripts. And of course, imagine how you might compose this script with another script that, say, only counts the foo calls such that the argument x is greater than 1. Right? I'm not going to be able to take this and just add on a little bit that says limit what you can do. You're going to have to come in and modify this script so that it's no longer composable anymore. You have to change the original script.
What happens if the program itself is concurrent?
This should still work. So GDB will still be. Oh, I see. You mean what if the stop handler and so on could be called multiple times? I
guess that's
I don't.
some kind
That really depends on the semantics of GDB. So I'm not sure what GDB does. OK, so to address these problems, we developed a scripting language for debugging, and the system that it's implemented in is called Expositor. And an expositor, an execution trace, is a first-class object. So instead of sort of being in the middle of the execution and stopping and starting and reading and writing, we pretend that the execution has already completed and we have it in our hands, and now we can compute over it. We view the execution as a trace, a list of snapshots, and now we can perform common list processing operations from functional programming to filter a trace, to map a trace to certain events in the trace, to fold over it, to count up the number of values, and so on, treating the trace as something to be computed over in a functional way. To implement this idea, we build on top of time travel debugging, and we use Laziness extensively. So time travel debugging gives you a way of treating an execution trace as a single object, right? I can go forward, backward. Basically, it's like a time-indexed series of events, and the time travel mechanism is an efficient way of going to this point, or this point, or this point, or this point in the execution without having to capture the entire execution and throw it to disk, which would be extremely expensive and very slow. So Expositor is implemented on top of GDB and UndoDB. UndoDB is a commercial tool that extends GDB with record replay time travel style debugging, and we basically just build on top of that by providing this functional programming interface. Okay, so for the rest of the the talk, I'm going to describe to you what the Expositor interface is. What is this programming language that we're providing, this abstraction of traces? What does it look like? I'm going to tell you about how we use Laziness in Expositor to implement these scripts efficiently. And in particular, I'm going to tell you about some data structures we had to invent to take advantage of Laziness in the right way. And then I'm going to show you some performance experiments that explain why this laziness turns out to be very important for efficiency and why these data structures are also important. And then finally, I'm going to tell you about how we used Expositor to debug a memory leak in Firefox, which turned out to be a data race. The interesting thing is the official fix in Firefox for this bug didn't actually fix the problem. They ended up adding some other trigger for the garbage collector when, in fact, they didn't need to do that, and they should have fixed this data race instead.
So the fix happened before you debugged this. That's why
we started to debug it, and a fix came in, but it was a non-fix. And then once we had debugged it, we realized the fix was the wrong fix. OK, so how do we count foo calls in Expositor? It's really easy. It's 2 lines of code. So basically, we treat the execution as a first-class object. So we have in our hands this variable, the execution. It implements the execution class that Expositor provides. And it has several methods, which I'll explain in a minute. One of them is the breakpoints method, which is, you can think of a way of filtering the execution of all possible events in the program to only those events, only those snapshots, those program states in which foo is being called. Okay? So, of course, under the covers, this is going to be implemented, you can think of as setting a breakpoint, running the program, having the breakpoint hit every time, and then remembering those states in the program, and then making those available in this resulting trace. OK, so once we have this resulting trace of all of the foo events, we've now filtered the execution down to those events. We can just compute the length of the trace, and we're done. We now have all of the foo events. OK, so 2 advantages that the other script didn't have. First of all, the control flow is straight line. It's very easy to see what this program is doing. And second of all, it's very easy to reuse and compose with other scripts. This is a purely functional. The execution and foo are immutable objects. So no matter what other computation you do, they're not going to be influenced by it. Foo is always going to be only the foo calls, and it makes no difference what other traces you might derive. And as a result, you can do something like filter all the foo calls to only those snapshots in which the variable x is equal to 0. And now I can count those instead. Oops. OK, so let me tell you more about the execution class's methods. So they're all listed on this slide. We've just seen the breakpoints call. There is also a call for system calls for checking read events or read calls or write calls or socket calls or things like that. The first line is the getAt line, and it says that you can, the getAt call, you can go to any particular time in the middle of a trace and get the snapshot at that particular time. There's also the watchpoints call that gives you all of the events where a watchpoint would be flagged. So you can set the watchpoint on a variable, and you can say whether you're interested in reads or writes to that variable. And again, that's effectively going to filter the execution down to only those snapshots where that read or write is happening. And then finally, you can also ask for an execution for all of the function calls or all of the returns. Now, the bottom 2 lines are for interactive control. So the way that you use Expositor is you'd fire up GDB, and you would say, I want to start running. And the program is going to run for a while. Now, the thing is, the program might be interactive. And so it's going to wait for the user to enter a bunch of events. So for our Firefox bug, for example, the Firefox bug requires you to scroll the screen on a particular test page, and then wait a little while and scroll the screen again. And then you can see the memory leak, and then you can see it disappear. And so in order to reproduce that bug and debug it, you're going to have to run the program for a while and manually do the scroll bar and so on. And then once you've gotten to the point where you're done, you can hit Control-C. And at that point, you now have an execution all the way up till that moment. And the execution variable will represent the execution up to the point that you hit Control-C. If you want to keep running, because you discover, oh, I need to do more work, well, then you can call continue, or you can call get time to run it further along until you want to stop and look at it again.
So I don't know much about how this undo DB thing works, but how does it do better than stashing the entire state? Can you tell me a little bit about how
OK, sure. So record replay is different than stashing the entire state in performing snapshots and logging the results of non-deterministic events. So the idea is that, let's say every 10 events, it will snap, we'll make it more than that, maybe every 1,000 ticks, it will record the entire snapshot. So you can snapshot, 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 snapshot. So in order to make sure you have a deterministic replay, all that's required is you record the results of system calls at every moment in between each snapshot. Okay, so every time you do a read, every time you take a signal, every time you do something that might affect a non-deterministic choice, UndoDB will remember the result of that event. And so when you call getAt, the equivalent of it in UndoDB, to go to a particular time, it will basically go to the furthest back snapshot preceding that time and then replay the execution forward, filling in its logged set of system call events.
Right. So like when you were saying earlier that you have those breakpoints of foo,
Mm-hmm.
you don't actually eagerly compute all the places where foo is being invoked, right? That would be very expensive.
So UndoDB will do that. If you set a breakpoint and you run the program, UndoDB will stop every time and capture all the traces, the breakpoints. But our implementation is lazy, and we will not do that. And I'll show you exactly how. OK. So these things will give you a trace. And a trace, as I said, is basically a list of you can view it as a list of snapshots, where a snapshot is just in a program state that you can use standard sort of debugging commands to look at its variable values and chase pointers and everything else. OK, so now given a trace, you can perform more computations on the trace. So for example, I can ask for the length of a trace, and that will compute the total number of items. I can go to a particular point in the trace by calling getAt, getAfter, or getBefore. GetAfter is saying, because the trace may be very sparse now, if you give it a time, it may be that there's no event at that time in the trace. So getAfter will give you the first one after that time, and getBefore will give you the first one before that time. And then the next three are basically functional programming things. So filter is going to filter the trace events according to this predicate, and map is going to map each event according to the function f to this new value. So for example, you could imagine having our trace of all foo calls, and we could call map on it to make a trace of, say, all of the values of the first argument to foo. Okay, you could call the getVar thing on the snapshot and then create a new trace of just those argument values. Yeah?
So I didn't understand the thing with getBefore. You were saying if I could call getBefore with a particular time index, and there may not be a state at that time index, and so
yes.
Why would there not be?
So imagine I did, let's say I'm doing the Firefox example again. So what will happen, the way we do it is we ran the Firefox example, we do the first scroll event, which is going to cause the memory leak to happen, and then I hit Control-C. And then what I do is I say, what's the current time? So there was this execution get time here. OK, now I have a value that's at that current time. OK, then I'm going to say continue, and I'm going to keep running it. I'm going to do the other scroll event. I'm going to hit Control-C, and then I'm going to do get time again. And me, the programmer, I'm going to squirrel away those values of those times. Say it's 100 and 110, whatever that is. OK, so now what I might do is I might want to filter the entire execution to be only calls to the garbage collector. OK, so now my trace only consists of those calls to, in this case, JSGC. Now what I'll do is I'll go to one of those times whose values I got, and I'll say, give me the most recent call prior to this time where I called the garbage collector.
The because you're filtering it, you may lose some of the snapshots.
That's right. OK, and then this is just this last line is emphasizing what I said before, is that traces are immutable, that they're defined. Yeah, they're immutable. So there's no way to add or remove elements to a trace. They're just defined as relative to an execution. OK, so how do we implement this? We implement it lazily. And the trace data structure is such that when you call something like the execution breakpoints foo, nothing is going to happen. It's basically going to make a thunk that when the thunk is queried, will actually perform some of the computation. So the way the trace data structure represents this idea is we're going to have this dotted box. And at the beginning of the box is the beginning time that the box represents in the trace, and the right-hand side is the end time. So when we start off and we create this thing, the box represents the entire execution, and we know nothing about it. We haven't forced it yet. Now, unlike normal lazy implementation of lazy stuff, where you just have a thunk and you push it, you run the thunk to get the value, our trace thunks are going to take as an argument a request to either do a get before, a get after, or a get at. Okay, so we're going to pass a time, and we're going to pass whether we're going forward or backward in time, because it's the get before and get after that's effectively going to force the trace. So let's say that we do that. We want to find out, well, at time 100, what's the most recent value of this trace for all of these execution breakpoints at foo. So the way that will work is this way. What we'll do is we'll pass in get before and 100 to our thunk, and it will go to time 100. It will tell undoDB, go to time 100, and then it will say start running backward. It will set the breakpoint, because it will have remembered that when I created the thunk in the first place. And it'll start running backward, and it'll say basically keep on running until you hit the first call to foo, running backward starting at time 100. So what will happen in this case is, let's say that foo is at time 50. It will go to time 100, run back to time 50, find the call to foo. So now it knows two things. It knows that there are no calls to foo between 50.1 and 100. So we'll make a node remembering that inside of the trace data structure. There are no events here. And it will also know, hey, there is a call to foo at this time, and it will cache that call, that snapshot, and store it here. Okay, it knows nothing about what happens after time 100 or what happens before time 50, and so that's represented in this data structure. These things are unknown. So if in the future I then wanted to call, say, get before 25, well, it's going to operate on this data structure now, this somewhat expanded version of the foo trace, and it will come over here and discover, oh, there's nothing here, and it will do the same trick. It'll go to time 25 and push back. If instead we said, oh, get before 75 after this, well, it's just going to go straight to here and then go straight to foo, knowing that I've already computed this and then I'm done. Yeah.
So it seems like get before and get after are the primitives. So let's say I wanted to implement filter. Is that like a subroutine in your system that you implement it using get before, get after?
So filter will basically layer on top of these things. So you can imagine what will happen is I'll do this, and then I'll do filter, and then I'll call a get before or a get after. So if I did a get before on a filter, that's basically going to push down to finding to the base trace, and it's going to start working backwards to find events, which it will then test against the filter and keep going until it finds one that's acceptable, and then remember that event. Right, so basically filters and maps and so on are just going to compose on top of these raw traces at the bottom. And when we try to force a filter, we're going to end up forcing parts of the underlying trace as well as parts of the filter above the trace. And the same will go with map and slice and everything else. Okay, so that's basically the simple idea. So there are more complex operations that we perform where we're, for example, going to merge traces together. So why might we do that? Well, imagine we have a trace that we have all the calls to foo, and we also care about all the calls to bar. Okay, we have to set those as separate breakpoints, and the way we'll do that is we'll create the breakpoints for foo, the breakpoints for bar, and then we'll merge the traces together. And merging happens according to time ordering. There's also this trailing merge call that allows us to combine together elements of two traces. Scan, which is basically like a fold, except it stores its accumulator results at each moment in the trace. And then tscan is sort of a version of fold that takes advantage of a lazy associative operator. So here's how those things are implemented. So if we call tr0 merge of f on tr1, I want to merge trace 0 and trace 1. If the two traces events are distinct, so the calls to foo and calls to bar, okay, no problem. Then the resulting trace, which is shown on the bottom line, is just going to have all the events from both traces. Now the only interesting case then is when you have two events that are at the same time. In that case, you're going to compute the result of the third trace by taking the arguments of the first two traces. So for example, if we were merging, let's say we were merging traces of all of the foo calls where we looked at all of the values that were greater than 0 and all of the values that were greater than 1. A whole bunch of those things are going to match up, and f is going to disambiguate those, and the case where it's only greater than 0 but not greater than 1 is just going to flow directly down. Trailing merge is going to take two traces, and it's going to compute the result in the third trace by looking at an event in the first trace, an immediately preceding event in the second trace, and computing the result in the third trace. And then likewise, all the way across. And trailing merge is, rev trailing merge is just going to do the opposite. And I'm going to show you in a minute an example of how this is used so you can see why you would care about this. I just want to emphasize, remember that traces are not only lists of snapshots, they're lists of any values, right? Like the example that I gave you with map, you might take a snapshot as an argument. Executions will always produce traces of snapshots, But from that moment on, you can produce traces of anything else. You could map the traces of snapshots to a trace of integers by just pulling off the first argument of every call to foo, for example. So this function f might be combining things, right? If I had, I don't know, I had a trace of all of the first arguments to foo and a trace of all the second arguments to foo, well, all of those trace values are going to be at the same moments in time, and the function f could just add the arguments together, for example. Okay, so the other computations are the scan and rev scan. So this is like fold. Okay, so that's what it's showing here on the bottom. You're going to take an accumulator and the original event, compute some function of those two. That's going to go here. And then this accumulator will feed into the call to f for the next element and store the result there, and so on all the way down the trace. So normally a fold in functional programming only gives you the end result. And this fold is going to store each intermediate result in its own trace at the same time that the original trace elements were stored. Okay, so scan, it's actually a standard Python function that we bring to this context as well. And revscan just goes the opposite direction. TR-scan, or tscan, stands for tree scan. And basically you can think of that as just an associative, an infix operator that's associative. So the resulting value at a particular n is just going to be f applied to all of the values before it, where you could compute them in any order, right? So if I had 4 values, I could have computed f of the first 2 and f of the second 2 and then f of those, or I could have done it the way that it's shown there. And the idea there is it gives you more flexibility in incrementally learning, materializing the contents of a trace by taking advantage of an associative operator. Okay, so those are the basic operations. And now I'm going to tell you a little bit more about how laziness interacts with those operations and how we try to take the most advantage of laziness in the interface. Okay, so let's say, for example, we're going to count the number of calls to foo x from the end of the trace all the way back until I see a call of foo 0. Okay, so basically you can think of the trace as a whole bunch of calls to foo. At some point there's going to be a call to foo 0, and I want to know, well, how many calls to foo happen after that point? Okay, so what this is going to do is it's going to first of all create the execution breakpoints for foo. It's then going to call scan and call this function with a non-zero foo, and the accumulator is going to be 0, so it's doing the fold. Okay, so inside of the fold, it's going to read the variable for the snapshot x, and if it's not 0, then it's going to increment the accumulator by 1, which is right here. Otherwise, if it is 0, then I need to reset the accumulator because now I've seen a foo 0. So I only want to count the things that happen after the last foo 0. So by the time I get to the end, I've reset the accumulator the last time, and I've only ended up counting up here the calls to foo after that last reset. Okay, so notice that the accumulator here is lazy. So I called this lazy accumulator, and the programmer explicitly calls force here to force the lazy computation. And why is that? Well, the reason is that by the definition of the scan, I'm going to call f on the previous accumulator and the current input value. And if the accumulator were not lazy, I would be effectively forced to go all the way back to the beginning and compute f for the entire trace, even if I could conceivably compute the result of this call without having to do that. So in particular, one way that I would like to be able to compute the result is to go to the end of the trace and go backwards in time and basically stopping at the first moment here that the accumulator is 0, and I don't need to compute anything about the prefix of the trace anymore. And by making the accumulator lazy, that's not possible. Okay, so now here's our first big example of how we can use Expositor to write a generic script. And this is a script that's going to find stack corruption in any program. Basically, the idea is if your stack has been corrupted, then the return address that you wrote when you entered the function call might be different than the return address that's there now when you're about to leave it. And so we'd like to tell when that happens. And the way that we're going to do that is we're going to write a script that maintains a shadow stack so that it will mirror the execution stack. And we will make sure that the shadow stack and the real stack are always matching up during the execution. The first time they don't match up, we'll know what the address was that was overwritten. Okay, so the first call here says, give me all the calls and all the returns, and then merge them together. Okay, so now I have a trace of all calls and all returns to every function in my program. And the shadow stack is just going to create for each one of these events the stack at that location. So ret adders just lists all of the return addresses of the stack in that snapshot. Okay, so now this shadow stacks trace has the stack at every call and every return in the program, every function call and every return. Okay, great. So now I'm down here with corrupted, finding the corrupted addresses. What I'm going to do is I'm going to call trailing merge on this function up here using the shadow stacks as an argument. And what's that going to do? Okay, well, this is the snapshot at a particular moment in the program execution, in the call rets. And this is the shadow stack at that moment. What we're going to do, assuming that there is a shadow stack, this is only going to happen, it's only going to be none in the very first function call that you haven't had a shadow stack. What we're going to do is we're going to compare, this is a trailing merge. So trailing merge is going to take the current call in the program and look at the immediately preceding call in this list here. So what it's going to do is at each call, it's going to look to the immediately preceding call or return in the shadow stack. Or each return, it's going to look to the immediately preceding thing in the shadow stack, which is the call. And then it's going to compare the return addresses for the snapshot with the return addresses that are shown in the shadow stack. Zip is only going to look at up to the prefix, right? So one of these is going to be one shorter than the other. If the immediately preceding thing was a return, then the call is going to have one more return address than the return did. If the immediately preceding thing was a return, then it's going to have one less. So it's just going to look at the prefixes and make sure that those are the same. And if they're not the same, then there's a potential problem. In that case, it's going to remember the stack that failed. Otherwise, it's going to return none. OK, so let's see how we could use this script. We're going to start off with running a program, TinyHTTPD, that we developed. This is an existing open source program. And for our security class, we modified this program so it had a stack smashing it had a buffer overrun in it that you could hit with a stack smashing attack. So we wrote a stack smashing attack for it. We start running this program, so we call the execution continue. And it's now running on this port. In a separate window, we call our exploit function, which connects to the program and does the stack smashing attack, which now it pwns my computer. In the debugging window, I hit Control-C. And now I call the stack corruption function, which is the code that I just showed you. OK, so now I have a trace where all of the elements in the trace, if there are any, have the address of the stack has the snapshot of the stack that was corrupted. OK, so what I'm going to do then is I'm going to get the current time for the execution, and I'm going to call get before the current time to find the most recently corrupted stack address. Then what I'll do is I will set a watch point on the last corrupted value, right? So I'll look at the last corrupted stack address, and I'll look to find out where that value is written. And then I will call get before the time when the corruption took place to find where the value was written. And now I found where my buffer overrun vulnerability is. OK, so the key to see here is, first of all, this wasn't very much code to write this out. We're taking advantage of all these nice facilities of programming with lists and so on. It's completely reusable. You can use the script to debug stack smashing, any sort of stack corruption on any program. It's not specific to this TinyHTTPD program. And the other thing that's really nice is that because I'm running what is effectively a dynamic analysis as the script inside of an interactive debugger, I get to interact with the results, right? So I don't just run the stack corruption and then get some address and say, now go figure it out. I now have my hands on the execution in which it took place, and I can start querying the execution and running additional scripts. So here I set a watch point, and I go back and I find out where the corruption actually took place. If there was a bug and I want to figure out why there's a bug, I can continue to interact with the execution trace using these scripts to help me learn more and more information. As another example of a reusable script, for the Firefox case, we developed a simple happens before data race detector to help us discover this problem. So that's, again, a reusable dynamic analysis. But the thing that's great about it is that when it finds a bug, you immediately have all of the power of an interactive debugger to start figuring out why did it happen. Whereas if you write a one-off dynamic analysis tool, it's going to say, oh, you have a data race on line 27 involving variable x and these two other threads. Go figure it out. Here you can figure it out immediately by starting to interact with the debugger to help you understand why it might have happened. Okay, so that sounds good. Now, thinking ahead to other sorts of scripts we might want to write, we're going to want data structures.
But I have a comment about that last thing you said.
Yes.
So isn't it true that there is a significant overhead to having this be turned on, say in a test case which is supposed to exhibit a data race? So one of the problems that people often complain about these dynamic data race detectors is that the overhead is so high that it messes up all the scheduling, and then you start generating these weird behaviors that don't happen normally.
Yeah.
That's still a problem, right?
It's still a problem. In fact, it's worse because the debugger is much slower. But I think that this is what you want. So I would say that our goal here ought to be not to give up on it, but to figure out how to make debuggers better. I mean, in my experience, I don't know about the Windows debugger. I hope it's better than GDB. I mean, GDB is kind of a crap debugger, to be honest. And I'll talk more about ways in which I would hope we can get closer to making this vision a reality by driving the performance down. But it's not going to eliminate the problem that you're talking about. Okay, so another sort of analysis that you might like to perform when you're writing a script involves data structures. So for example, if you wanted to debug a memory leak, you might want to keep track of all of the things that are current. You might want to have a sort of a shadow data structure that represents all of the malloc data. So every time you malloc something, you add it to your set. Every time you free it, you remove it from your set. And at some point in the program where you expect or you know something about a leaked value, you can look in your set and then, oh, that's the address, and then start doing the same sort of stuff I just showed you. So therefore, we need a data structure. We need sets, maps, hash tables, multisets, things like that in order to program with. Okay, but the problem is, if we just use Python's data structures, we're going to end up compromising laziness in a similar way that we might have compromised it if we hadn't made scan and fold and so on lazy. So let me show you why that is. So here we're going to write a program that's going to collect all of the arguments to all the calls of foo in a Python set. And what's going to happen here is I'm going to compute all the breakpoints. I'm going to scan, so that's like a fold, by collecting all these arguments in the empty set. And then at the end, once I've gotten all the way to the end, I'll look in the very last, I'll look at the most recent to t value and ask whether 42 is in the set. Okay, so what is collect foo args going to do? Well, it's going to force the accumulator, so that's the set, starts out as empty, and then it's going to union it with whatever the current value of x is. Okay, so why is that a problem? Well, the problem is that each time I go to perform this union, I'm going to then, first of all, I'm forcing the trace again, so I'm going to have to go all the way back to the beginning. And second of all, union is going to deep copy the set each time I add an element to it in order to make it purely functional. Okay, so you're going to get killed on performance both because of the deep copy and because you have to go all the way back to the beginning, even if it turns out that the last thing, maybe at time t, just before that, you stuck 42 in the set. And so therefore, we don't care anything about what happened before it, and yet you're still going to be forced to go all the way back to the beginning to compute the entire set. Okay, so we invented a data structure called an edit hash array mapped trie, or EditHAMT, which is a lazy immutable set map or multiset multimap. Each update is going to share structure with the prior EditHAMT, and only when you do lookups are we going to force the necessary computation, so it's lazy. And the implementation of it is going to involve an edit list and a lazy variant of a hash array mapped trie. So hash array mapped tries exist. Those are not a new idea. Edit lists exist. Those are not a new idea. But combining these two things together, that's the new idea, and applying it to this debugging context. OK, so now I'm going to force you to think again, and while I explain to you how these data structures work. So if you don't want to think, you're going to have to zone out for 10 minutes. But otherwise, I'm going to do my best to explain to you how it works. OK, so what's an edit list? An edit list is just, instead of maintaining the actual values inside of a set, it's going to maintain all of the operations on the set. So every time I add an element to a set, instead of actually representing the set as that value, and then removing it, representing it as the empty list, and then adding this, representing it as a list, I'm going to represent the entire thing as this list of operations. I added this, I removed this, I added this. When I want to look up whether something is in there, I'm going to go to the most recent thing, and I'm going to keep going back until I either find a find or a remove. The first one of those things I find will tell me whether or not it's in the set. So if I find a remove, it's not in there. If I find an add, it is. OK, so why is this a good thing? Well, in our case, we actually care about each of these. We're separately maintaining each element in our trace is going to be the complete set. So we really need, at time t0 this, and at time t1 this, and at time t2 this, right? We need a cheap way of representing all of the possible incarnations of the set throughout the entire trace. And an edit list is a cheap way to do that. Now the drawback of an edit list is that lookups aren't O of 1 anymore. They're now, you have to move your way back inside of the trace. And I'm going to show you how we overcome that problem in a sec. Oh, and these dotted lines are saying that it's lazy, that the previous things are lazy, and I'll show you in a minute how that comes into play. OK, so now what's a HAMT? So a HAMT is a hash table tree hybrid. You can think of if you think of a chained hash table as an array, right? You hash into all of the elements of the array, and then you have a list of buckets for dealing with collisions. Well, in a HAMT, the array is going to be an AMPT, an array mapped trie. So I'm going to get rid of the actual array, and I'm going to replace it with this array mapped trie instead. And then instead of maintaining a list of buckets for resolution of the hash collisions, I'm going to do double hashing. I'm going to basically have another HAMT that resolves cases where I have a collision. So if I hash two values and they end up going to the same spot in the AMPT, then what I will do is I will have a new hash function that then that distinguishes those two values in a nested HAMT that I use to resolve chaining, or to resolve the collisions. OK.
You may collide on them again, right?
Right, and you just keep doing this all the way down.
Okay.
You just keep doing the nesting, yeah.
And you have a whole bunch of hash functions. Right?
You end up having a whole bunch of hash functions. So it turns out we're not, in our EditHAMT, we're not going to end up doing this nested HAMT business. So don't get too fixated on it. But a regular HAMT, which is not our idea, that's the way that they would propose to resolve collisions. We're actually going to resolve collisions with edit lists in our final version. OK, so what's an AMPT? An AMPT is just a representation of an array as a tree. And it's a map from integer keys to values. So the internal nodes are sparse arrays. Basically, what you're going to do is you're going to break up the key space into n-bit values. And you're going to have you're going to have whatever the total key length is divided by the number of size of the bits. That's how many levels you're going to have in your tree. And the leaf nodes then contain the bindings. So as an example, let's say I want to do find 7 inside of this particular array. Well, 7 in binary are these three pieces. These things are 2 bits each, right? So they represent 0001, 1011. And what we're going to do is we're going to iterate through the key space, moving through this array. If we find a pointer in the array for this particular key value, then we'd follow the pointer. If we don't find it, then we know that the value is not in the list. It's not in the array, and then we're finished. OK, so in this case, we have 00. So that's here. So we're going to follow the array. The next thing is 01. So then up, we see this. So we're going to follow it. And then finally, we see 11, which is this. And we see, indeed, 7 is mapped to value B inside the array. Now, if we were going to 50 here, we would end up breaking up the key space. And we would have, again, 000. I guess in this case, we would have 11 is the first of the key for 50. Plus, it would have other elements of the key. But in this case, those other elements are not actually in the tree. So looking up 50 immediately leaves us to this leaf node. And we can look up 50 and say, yeah, it's in the tree. And then we're done. So in the worst case, you're going to end up going to the completely bottom part of the tree. But the tree is a fixed height. So essentially, you still have O of 1 lookups. Right? It's based on the length of the key. OK, so a lazy AMPT is a lazy variant of this, where the internal nodes are lazy sparse arrays. And again, the idea here is that these arrays are going to be computed as they're needed, where the laziness is essentially inherited from the laziness in the trace data structure. And the nodes are going to be lazily created during lookup. So a way to think about this is when we go to insert something into the tree, we're going to create a thunk that will work its way down the existing tree to find out whether that thing is already in there. And then resolve the hash collision and everything else. Or if it isn't in there, it's going to then cause this tree to then be materialized. And it's going to share internal nodes. So in this particular case, if we inserted 57, we would say, oh, well, I'm going to go to this first element of the tree. I'm going to need to go to the right here, which means I need to inherit this version. So this is lazy. But it's not actually going to it may be that this node was not even materialized in the original tree. So this is going to be sort of a lazy pointer to that node if it was eventually forced by, say, looking up that node inside the tree, et cetera, working its way down here and eventually sticking 57D in. Along the way, we just discover that here's where 50 would go, and so we insert that in the tree. Okay, so the point is, rather than eagerly computing this tree when you do the add, you're going to just take a thunk that will compute this tree whenever you force it through a lookup. Okay, so an EditHAMT is an edit list plus a hash plus a lazy amt. Okay, so the chained hash table is the EditHAMT. The hash key lookup is the lazy amt, and the hash collision resolution, instead of being nested hamps, is going to be edit lists. And it turns out the edit lists are also going to be useful for a remove operation. Okay, so here's an example where we start with an expositor trace. And let's say, for example, at each element in this trace, we're going to add these elements A0, A1, and so on to our resulting trace. Okay, so the way that that's going to work is at each moment here, we're going to create the thunk that represents the process of adding or removing or adding an element to the trace. In this particular case, we added A0, and this is where A0 would go. Here we remove A0, and again, that removal is then just going to chain with the add that was there before because these guys hash to the same location. In this case, we're adding A1, and so it's going to go a different way, and it has nothing that's previous to it. All of these arrows and so on are all lazy, so you're not going to see them until you actually start forcing things to happen in the computation. So you can see here how edit lists are dealing with removals. So this is hashing to the same value, and it's augmenting what was there before. But it's also going to deal with collisions. So let's say, for example, that A5 happens to collide with the same place as A0. Then all that's going to happen is here is going to be add A5. And then in order to look up A5, I'm just going to have to traverse my way down the edit list until I find A5 or I hit none, just like you would have with a bucket array in a regular hash table. OK, so I'm just going to skip this. OK, so I hope you get at least the basic idea. So let's see now how important this is for performance. We made a micro benchmark that looks to see how effective this is. And the way the micro benchmark works is we're going to run a program to create a trace. We'll then call getAfter or getBefore to enumerate all of the events from the trace. So the trace that we're going to look at in this case, I'll show you in a moment, is a bunch of function calls. We'll create the trace and we'll call getBefore to find all the events, or getAfter repeatedly to find all of the events, to force each one at a time, therefore incrementally lazily expanding the lazy trace. After we do that, we're going to repeat for trace 2, where trace 2 is derived from the same input as trace 1. So it should be able to take advantage of the materialized laziness, and things should be computed faster because it doesn't have to force all of these thunks anymore. OK, so here's the test debugging target program that we're going to use. Inside of this program, it's a couple of nested loops. There's calls to the function foo here and calls to the function bar here. Foo takes 2 arguments x and y. Bar takes 1 argument z. Generally, we're interested in these calls to foo, so we're going to get foo traces. But we may also be, in some cases, interested in calls to bar, although mostly they're just there for filler. OK, so here's our first benchmark. We're going to capture all the breakpoints to foo, and then we're going to filter based on all of those things that have even first arguments versus all those things that have odd first arguments. OK, so we make 2 traces that are derived from the first execution. All right, and here's the performance results. OK, so let me explain how all this looks. First of all, time 0 here is where we create trace 1. Then this sequence is, imagine that I have a loop that's between trace 1 and trace 2 that's continuously calling getAfter until we're finished to get all of the events. That's this side. Or is continually calling getBefore by starting at the end of the trace on all the events. That's this side. Okay? So this is the first call to getAfter, the second call, the third call, and so on, all the way up until we've captured every call to foo. And we do that first for trace 1, and then we rewind the program and we do it again for trace 2. So trace 1 is going to force everything to happen for the first time. And then we're going to create trace 2, and then we're going to query trace 2 again. Okay? And it's the same on both sides. The y-axis is the cumulative time to perform all of these events. OK, so what are the different lines? So the baseline is just the time to simply start up running GDB. OK, so that takes almost a second just to start up GDB, so we don't want to count that time. The lazy trace is regular expositor in the way I've described it. Strict trace is expositor with all the laziness disabled. So all the problems of not making things lazy that I use to motivate why we use laziness are going to be evident in this trace. And then finally, GDB is just doing it with GDB Python scripts, doing it in this sort of non-reusable, non-composable way. And then undoDB is using the same thing as GDB, but instead of restarting the program for the second trace, which is what you have to do with GDB. Once you've run the whole program, you have to restart the program to run with the second trace. With undoDB, you can rewind the program and rerun it, which, as it turns out, will improve time a little bit. OK, so lazy trace has a low trace creation cost. Basically, it is costing you essentially 0 here. Notice that the time of creating it is basically nothing has happened. Now, on the first query, all of a sudden, we're going to pay this cost to start up GDB and run it. And we're going to eventually work our way over here, materializing all of the events. Okay? So the places where there's a steep curve here are all of the calls to bar that have nothing to do with any call to foo. Okay? So it's going to take some amount of time, but no events of interest have taken place inside of that period. Right? So in the case that all the foo events are even, I'm going to capture all the even foo calls, and then there's a bunch of odd foo calls that I'm going to need to skip over. And that's what's happening in these steeper curves, because there's no event of interest there. But you can notice that basically the amount of time that's taken is the same, looking up on the y-axis in both of those cases, because I'm pushing through the same number of events. The lazy trace works faster than just vanilla undoDB or GDB for the first third of the queries. So that's good. The slope of the trace in the second query is much shallower, because I've already materialized all the lazy events. And so I end up just getting to reuse all of the stuff I saved. And notice that the undoDB curve is below the GDB curve, so it's faster to rewind and go again than it is to restart. Finally, notice that the strict expositor trace up here is always worse than the lazy trace. So forcing all the computation is a worse thing to do. And then finally, reverse execution is slower than forward execution. And so that's why this graph looks basically the same, but it's just stretched upwards, because running backwards is slower than running forwards. But the same trends apply.
So are you implementing the laziness with some runtime support yourself, or is it all just implemented inside Python?
It's all implemented in Python.
So you're really implementing lazy thunks in the sense that once you claim it, you stash the result and use it again. Okay.
Yes, that's right. OK, so the second benchmark illustrates the use of EditHAMTs to improve the situation. And what we're going to do is we're going to create a trace of EditHAMTs mapping Z to snapshots of calls to bar Z. Okay, so every time bar is called with 1, I'm going to have a map for key 1 in the EditHAMT to all of the snapshots in the trace that have that as the 1 as the argument to bar. Okay, now that I have that trace of EditHAMTs, I'm now going to create a trace of events when foo xy is called, such that the snapshots of calls to bar Z have y equal to Z. Okay, so what I'm going to do is I'm going to look up in the EditHAMT the previous thing, and I'm going to compare it to the current call of foo. So if my EditHAMT contains all of these, well, this is not showing the EditHAMT, but if it contained, this was my trace, then when I see foo 1, 2 here, I'm going to pull out this call to bar 2. When I see bar 3 here, I'm going to see these things are the same and create this trace here. Okay, so I'm going to be computing all of these things in my EditHAMT, and then I'm going to go through and post-process them to find these events that I care about. Okay, so what this shows is that I'm going to use lazy trace again, which uses a regular EditHAMT, and then I'm going to have this strict map where I use the Python map function instead, which is going to force me to materialize all the trace. And what we can see is that when we're forced to materialize all the trace, the performance is crappy. It's basically going to cause us to go, every time I force the trace at a particular moment, I'm going to have to recompute the whole thing from scratch at that moment. I go to the next moment, I'm going to have to recompute the whole thing from scratch again, and so on, which is going to cause the time to be really awful here. In the case of Expositor, we're going to get this nice slope here from laziness that won't require us to have to do that. And in fact, we're faster than just GDB with no expositor overhead for the first half of the queries. And once again, the get before is a little bit slower. You can see this line ends up here. For the lazy map, where, yeah, it's much worse. Okay, so here's my concluding technical information slide, which is how we used Expositor to debug this memory leak in Firefox. So basically, the problem with the memory leak was that there was a trigger to run the garbage collector to give back memory to the operating system. And the trigger flag is set at various moments. And it can be set for multiple threads. So there's a lock that's guarding this flag. And one particular place in the program that had to do with an event handler set the flag without acquiring and releasing the lock first, and caused the flag to get corrupted so that the garbage collector was not called until some later time. And the way that we figured that out is we sort of systematically started testing hypotheses. So we figured, OK, a memory leak probably has something to do with the GC. So we first of all made a trace of the garbage collector behavior. We got all of the calls and all of the returns to the garbage collector. So all the calls are the breakpoints to JSGC, and all the returns are JSGC where the index is -1. That's saying, give me the return snapshot. And then we did a merge to merge these two snapshots together so we get the calls return, call return, and so on. Now, in the order of events, when I run the program, I do the first scroll, and that starts the process of allocating a bunch of data. And then I do the second scroll, after which eventually the data is removed. So those are shown at these 2 times in the program. And we did the Control-Cs, like I said, to give us times in between those 2 times. OK, so when looking at these things, we also realized that the problem was that memory was not going back to the operating system. So we also wanted to track the calls to mmap and munmap, which is the way Firefox brings memory into the process and takes it out again. So here we see there are a whole bunch of mmap calls to allocate a bunch of memory. And here the garbage collector is called, but notice that none of the memory is getting freed. So then the garbage collector is getting called again, it's getting called again, and then eventually we see the unmap calls here that makes the memory go away. So the question is, why didn't the memory go away sooner, but it took several of these calls returns before it eventually went away? So after looking at the way things were working, we hypothesized that we noticed that the garbage collector was being set to run by a trigger. And so what we did is we looked at these timer events that Firefox sets to set a timer, wait some amount of time, and when the timer goes, to run the garbage collector at that time in the future. So here's where the timer is set, and here's where it eventually runs. And we used an EditHAMT as a shadow data structure to map calls for when the trigger was set into when the garbage collector actually runs. And so you can see here, here's the trigger set. Here's the garbage collector running. That's where it is here. After we call the GC, it sets this trigger again, which then it triggers the next one, and then it triggers this, which triggers the next one, and so on. And then eventually this free stuff happens. OK, so we discovered that there was this variable that says whether there are chunks that are waiting to expire or not. And a bunch of these events were happening in these locations. And we looked at the code, and we saw that when those events are happening, it ought to be the case that the munmaps are called. And we tried to figure out why that was. And then we saw that there was this variable that was set for multiple threads. So we hypothesized maybe there's a data race on this variable. So then we wrote a simple happens before data race detector that we call onelock. So we know it was protected by one lock, and we know it was one variable. So we wrote a data race detector that just was on the one variable for the one lock. And we discovered, sure enough, that there was a data race there. And then that revealed what the bug was. OK. OK, so there's a bunch of related work. Our design was inspired by functional reactive programming. So the idea of functional reactive programming is that instead of using callbacks, you can have time-varying values. So you can think of our traces. In fact, other people, this tool Mistake, uses functional reactive programming for the purpose of debugging, where basically you're going to have your scripts, and you're going to call your script every time an event happens, and it's going to process it through the entire execution of the program in a similar way to our filters or maps or folds are working on side of Expositor traces. The main difference is that with functional reactive programming, time always marches forward. So there's no way to go to particular moments in time, to learn what times are, to go backwards in time. And all of these things are useful during the debugging process, and you don't have them available to you in the FRP style. You also don't have laziness, and so you're going to end up potentially computing lots of stuff that you really don't care about. Time travel debuggers, we build on top of these. We're agnostic as to what kind of time travel debugger you provide, although it seems like replay debuggers are more efficient than logging every instruction. You could view our traces as a way of querying a stream, right? You're filtering it, you're mapping it, and so on. It's a stream query. So you could look at all of the research literature on just regular querying of streaming data sources in databases. In the case of programming languages, there are two projects, PTQL and PQL, that look at writing queries over program executions, which they implement via compilation. They do it with dynamic instrumentation. So I think that's great. I would think you could compile these languages down to Expositor. I would say the main disadvantage of doing that is Expositor is going to be slower than dynamic instrumentation. I would say the main disadvantage of dynamic instrumentation is that many programs are non-trivial to build. And so if you have to compile by dynamic instrumentation, you have to rebuild your program every time, and that could be very slow. How long do you think it takes to build Firefox? Just a guess. It takes an hour to build Firefox. So every time I'm interacting with the debugger, if I want a new trace, I have to wait an hour to recompile the program. Okay, so I probably don't want to do that. On the other hand, again, you're going to get better performance. So it may be that there are some usage models. One possibility is you could imagine using this log every instruction idea to log everything. And then once you have it all, computing locally within a logged trace is going to be much faster, I think, than using GDB and undoDB. So there's probably some interesting trade-off there. But I would say that the main limitation of Expositor right now is that the speed with which it can process events is limited by the speed with which GDB and undoDB can provide them, which is very slow. Like it can process thousands of breakpoints per second. Okay, well, thousands of breakpoints sucks. If you want to implement a race detector, you care about every read and write to a particular variable. It's very slow. Like I think just to find this one data race where we knew roughly where it happened, and we went just backwards from that moment in time, and it didn't go very far back in time. It took like 30 seconds to find this bug, whereas it would have been milliseconds or less if you used an instrumentation-based tool. So really, we need a way of implementing faster watch points or breakpoints to do these more fine-grained analyses, and that's basically going to be part of our future work. Okay, so thank you for your attention, for listening to our approach to debugging, doing scriptable debugging on execution traces. The advantages of this approach: it's purely functional, and it gives you a way to build reusable, modular, and compositional scripts. There are two scripts that I talked about: the stack corruption one and the data race run. You can reuse for any program, and you can imagine lots of these scripts that explore problems with, based on function calls or look for memory leaks and so on. You could code up as Expositor scripts and reuse. And we use laziness for efficiency, and there you go.
Let's thank Mike.
Can you go back one slide?
So just to say, we're a little bit over time, so if people need to take off, then you should feel free, but Mike should be around for questions as well, if you want to stay.
So when you were comparing with these things like PQL, I was expecting you to say that you are nicely integrated with time travel debugging, whereas these guys are not. But
Yes.
you didn't say that.
Well, it's true. You're right. I was speeding through.
So, but that, to me, that is the most important aspect of your work, right? Because, for example, consider the problem of data race debugging. It's very hard to get a repro. Every time you want to find some other thing that happened in the past, you have to re-instrument and recompile and re-execute. What are the chances the same damn thing is going to show up again? Right?
Yes, that's right. So I would say that we have the same problem in getting the bug to happen for the first time.
Yeah.
And I would say you would want to compose with something like Chess or some other active testing tool to help you get the non-deterministic bug to happen while you're running Expositor. And then once you find it, yes, then you can interact with it and so on. And so that is definitely an advantage. But we still have the problem that you mentioned in the beginning of, well, you have to get the bug to happen, and we might confound that because of the slowness of running with Expositor.
That if you hook up with something that actually controls scheduling, like Chess or one of these active guys, right?
Yes.
Try to control scheduling, then the chances of, mean, then they do have a more abstract notion of causality there, right? And they're not just getting triggered by all these random timing sequences and so on.
That's right.
The chances of getting something that happens even in non-instrumented executions would be higher, I think, if you hook up with one of those tools.
Yep. I think another advantage that we're hoping to exploit in future work, I should have mentioned it, which is that this approach, I think, gives you a way of potentially integrating with other sources of information. For example, doing a static analysis on your program. Our vision for all of this is that static analysis, even dynamic analysis, and debugging are basically treated as separate things. You do this one, or you do this one, or you do this one. And there may be some translation between these that happens in the programmer's head, but there's no translation between them in terms of the tool suite. So what I think would be great is if you had some static analysis results that said things about the invariance between variables or things like that, you could use them. You could even use dynamic instrumentation to generate results that you could attach to these traces, right? So that this information was available to you in an end-to-end sort of debugging platform that takes advantage of all sources of information you can provide. So I haven't thought carefully about how we would integrate all of those things, but I feel like once you get to the point now where you can interact with a trace in this functional, reusable kind of way, it gives you this extra opportunity.
What are the requirements for using Expositor with the debugger? So, for instance, you used it with GDB. Did you try it with VMware's Retrace? And would it work with Windows Debugger?
I think it should work with those. All we really care about is that the underlying tool gives us a time-indexed representation of the execution. So those tools will give you that. I mean, you can just use the API that's provided by them to, essentially the way we did it with Expositor is we built a Python class that gives you this time-indexed trace, and then it calls the unDB calls and so on to give you that abstraction. I got to believe you can implement that abstraction for these other tools.
So you could substitute another debugger?
I think so, yes.
As long as it provides the right interfaces?
Absolutely.
Any other questions? No. I was thinking, you had this thing where if I did the execution and I said give me the breakpoints for foo and then give me the breakpoints for bar, each time you're gonna go back and rerun the thing to build the traces for foo and for bar, right? Do any of these debuggers, or is something that you're working on maybe gonna try to make the second execution faster?
It will be faster. It will be faster. So what undoDB does is it will, as I mentioned, it will cache. So it remembers the whole execution. So it doesn't actually rerun it. It will replay all of the system calls. And the replay of the system calls is much, much faster than actually running the program from the first time.
Just because the system calls go faster?
Yes, yes. Just because you don't have to do a trap to go into the kernel and come back again.
But all the computation is also, you should be able to just cache that and do it again.
Yeah, so undoDB is caching it. They're remembering a snapshot, and they're remembering all of the results of system calls. So that stuff is all cached. And when you go to rerun it, it's going to save all this information for you. And so it will make the rerunning faster. So one thing I didn't show you is, what's the space overhead of using this? So using a record replay debugger has potentially significant space overhead. And if you wanted to dial down the space overhead, then it's a direct space-time trade-off of how much stuff you're going to have to re-execute. The same goes with the laziness. So these performance experiments that I showed you are like 5 days old. And so we're still in the process of figuring out what the space overhead is. But I expect that it's not good. And that's going to be part of the trade-off. But we'll optimize it.
Other questions? No? Let's thank Mike again.